Hi, welcome back to the channel. This is structural analysis made fun and easy. So this is bearing capacity of a shallow strip foundation. What are the main differences between the soil test data required for the design of foundations on a clay and on a sand, and what are the causes of the differences? A surface strip foundation is to be placed at depth 0.3 meters in a saturated soil with the following properties. Cohesion C dash is at drain 4.75 kilonewtons per meter squared. Angle of shear resistance phi dash was 20. Bulk density equals 18.06 kilonewtons per meter cube. Use the chart of Terzaghi's bearing capacity factors given in figure 7.4 to find the maximum bearing capacity if the width of the strip is to be 0.6 meters. The groundwater level is known to remain at a considerable depth below the foundation. What assumption concerning the low distribution is made in the derivation of Terzaghi's bearing capacity factors? Let's see. CEI. Oh my. Oh, that's better. Solution. In general, a clay soil tends to be homogeneous, and for foundation design, its undrained shear strength is critical, since its bearing capacity will be lowest just after construction. In time, the excess pore pressure decreases and the soil strengthens. As this takes place, the soil consolidates, causing settlement of the foundation. The soil test data required for a clay soil are therefore its undrained shear strength and its compressibility characteristics. These can be obtained from laboratory tests on undisturbed soil samples in the laboratory. In the case of sandy soil, settlements will take place almost at once, and the amount depends on the relative density and the position of the water table. Sandy soils tend to be less homogeneous, and undisturbed samples are not easily obtained. This has led to the development of in situ tests to determine the bearing capacity and settlement characteristics, such as plate bearing test and the standard penetration test SPT. That's where you bang a cone on a steel shaft bar into the ground. So you've got equation 7.1 is generally referred to as Terzaghi's equation. Where's the 7.1? Oops. There we go, hold on. Equation 7.1 is generally referred to as Terzaghi's equation and may be written in the form. Okay, so 7.1 is this. 7.1. Q bearing capacity per unit length equals gamma B over 2 and gamma plus CNC plus Q dash NQ, where N, gamma, NC and NQ are known as the bearing capacity factors. Let's look at that again. Equation, alright, so QF equals CNC plus gamma ZNQ plus 0.5 gamma B N gamma, where NC, NQ and N gamma are the dimensionless numbers known as the bearing capacity factors. Their values depend on the value of the angle of shear resistance for the soil. What's that again? Graphs of their values have been produced by various workers, e.g. 4.7. Okay, so you've got the y-axis is delta degrees, is that? Values of NC and NQ. So you've got the x-axis, values of NC and NQ, and values of N gamma. 70, 60, 50, 40, 30, 10. So the values of NC and NQ go up almost, is that exponentially? those curves are interesting. Q is the capacity, B is the width, and Z is the depth. So circuits bearing capacity factors Q over B equals Q equals C N C plus gamma Z N Q plus 0.5 gamma B N gamma. Using the data figure given from figure 7.4, Ny equals, N gamma equals 2, Nc equals 12, and Nq equals 5. So what do they mean, and what are they based on? So it says, oh yeah, what's the 5.7 over 1? Substituting in equation 7.2, QF equals 4.75 times 12 plus 18.06 times 0.3 times 5. Where's the plus 0.5 times 18.06 times 0.6 times 2. So I know 0.6 is the width of the fan. Alright, hold on. Right, let's go through the, right, so the foundation depth is 0.3 meters. The foundation width is 0.6 meters. Cohesion is 4.75. Angular shear resistance is 20. Bulk density equals 18.06. What was it again? 4.75. Oh yeah, he said. So the QF equals 4.75 kilonewtons per meter squared, wasn't it, times 12? And the depth factor is CNC plus Z NQ plus 0.5. So that's 18.06 times 0.3, which is depth times 5. Plus the width factor, 0.5 times 1806 times 2 equals 94.9 kilonewtons per meter squared. And the bulk density is 18.06. That's where that is on there. Oops. Was it? I've lost the, oh yeah. So the width factor is 0.5 gamma B and gamma. 0.5 times 1806 times 0.6 times 2. The value from Terzaghi's chart are regarded as somewhat conservative. Values published for NC by Prant, NQ by Resnat, and N gamma by Hansen are preferred. Using these values for delta phi dash equals 30 degrees, NC equals 14.8, which is higher, NQ equals 6.4, which is higher, and gamma equals 3.54, which is higher. This represents the ultimate limit state of the soil before it fails in shear. Oh yeah, so QF equals 4.74. 4.74. Oh yeah, that's the cohesion, wasn't it? Times 14.8 plus 18.06 times 0.3 times 6.4. 6.4. 18.6 is the bulk density times 0.3 the depth plus 0.5 times 1806 times 0.6 times 3.54. This represents the ultimate limit state of the soil before it fails in shear. It should be noted that in practice, a foundation is 0.3 deep. Yeah, would not satisfy the building regs. Yeah, have to be 0.9, wouldn't it, minimum? The assumption about load distribution under the footing are discussed in example 7.3. Okay then, so that was a useful example though. Those about the bearing capacity, cohesion, and the depth and the width. Hopefully you found that interesting, and please like and subscribe, like the video and subscribe to the channel, and I'll see you in the next video. Thanks.